Here is my lecture on how to describe soils. This is going to go through the Canadian soil classification and all the little steps you have to do to describe a soil profile. We're going to try and do it in order so that when you're doing your report, your assignment, that you'll be able to do all the steps to describe your soil profile in order properly for your assignment. One of the first things I want to talk about before we move on to the soil profile itself is when you're out in the field, it's important to take good notes. That most field researchers, before they ever set foot in the field, they have done a ton of research at a computer or with a phone, and they know a lot about the site that they're going to before they get there. They've looked at maps, they've talked to locals, they've done the research. So they already know the general historical climate, the historical land use, the slope, the geographical area. They've looked at soil maps already. They have an idea. They're not walking in blind. This is pretty common practice for most field researchers. You're not just going into a field and figuring out on the fly. There is some of that as well, but a good field researcher goes in as prepared as they can. So those on-the-fly decisions are easier to make. Other things is trying to be consistent. You can't always do all the things that you want when you're working in the field. Things go wrong on you. But in our case, for soil profiles, we follow a very consistent soil classification system. So no matter what your conditions are, no matter what is going on out in the field, every person in Canada who's classifying a soil is following the same rules, the same orders, using the same words and same terminology so that everything is as similar as possible. This is the order that all of your profile horizon descriptions need to follow. So every soil pedon in Canada has been described using this system, where we always, for each horizon, we're describing the color first, then the texture, then if there's mottles, we talk about them, then structure, consistence, if there's roots, if there's pores, all of these extra things. It means that horizon boundary, which I consider quite important, is the third to last. But it's just, that's the order that is in that handbook and everyone follows it. So it's the order that this slideshow is going to go in right now, even though sometimes it feels a bit disjointed because we're going to talk about color of the horizons and back and forth. So make sure your assignment follows this order. Now, before we even get to our soil profile, I mentioned a good field researcher does the research that they can, records everything, record the habitat, because that's going to help you figure out what order you're in and what grade group you're in, because the orders are dependent on habitat. You're probably not going to have a forest soil like a podzol if you're in a grassy field. You might, it might be recently turned into a grassy field, but you're more likely to find a glade soil where there's been a history of water saturation. So in a beaver meadow or a wetland, right? Noting that habitat, that dominant vegetation is going to help you figure out what soil you have. We also need to note any signs of erosion we see nearby. That's part of classifying a peat properly, whether it's water erosion or wind erosion, whether it's been taken away or deposited. So these are some examples of different kinds of erosion. Down here that's behind me, this is a gully, this is gullied land. This is severely gullied land. This is like severely wind eroded. You're not going to see stuff like that typically. But if you can't see your profile because there's so much erosion, that matters, right? So looking for these signs of erosion, noting them when you're out in the field. If you happen to have an organic soil, then you should note what that organic soil is made out of. Is it mostly sphagnum moss? Is it mostly grassy materials? Is it mostly sedges and rushes? Is it all leaves? Is it all needles? Coprogenous is poop. So you should note what is on the surface, what vegetation is there, and if that differs from what the content of your organic soil is made up of. When you have organic soil, you are looking at how decomposed it is. So we'll talk about the von Post scale and how fibrous the soil is. When you take a ball of it and you squeeze it in your hand really, really tight, can you see those fibers? Are they strong? Does that soil stay in a ball, or does it just squeeze out between your fingers? So you look at how much of those fibers stay in that ball that you've squeezed. Here's our von Post scale. And I will at some point find an organic soil and show how this works in the field. I'll take a hike up to one of our organic sites and film this for you. Organic soils, true organic soils, are rare unless you are in a wetland that is quite boggy and old. You probably are just going to have an organic layer over top of a mineral soil. So most of you, this probably isn't going to be something that you encounter. Color is one of the key ways we identify soil profiles. So Munsell was just an art professor who got tired of the idea that color was subjective, that he couldn't classify soils. Your blue was not his blue, or more specifically, what shade of blue are you talking about? He wanted all the colors to have a numbering system, so you knew exactly what color you were talking about. So he broke up all the colors into a beautiful scale diagram here, where we have the value is how light or dark it is going up and down here. And then he has the color spectrum, like the Roy G. Biv, red, orange, yellow, going round in a circle. And then as you get further, you have gray in the center. And as you get further out, the chroma of that color changes. So he called the color the hue, whether it's red, blue, purple, green. He called the lightness and darkness the value, and then how true that color is. So from gray out to like a true color, he called that chroma, or color purity. This is an example up here of his actual color charts, and 5 being like middle ground. So 5Y, that's a pure yellow per se. 5P is a pure purple. He has these charts for every color, but in soils, we're only using them for specific color tables that we use with soils. So for us, this is a really common one, 7.5 YR. So that's halfway between yellow and red. You get yellow red. We tend to use 7.5 YR and 10 YR. Those are the ones that we end up using for our soils around here the most. You might have to use a different one depending on if you have a glade soil, or I have no idea what other soils you guys might have. But how it works is we know that the hue is 7.5 YR, so that's where it is in that circle. And then we want the value first, and they helpfully always show with the number and then the slash, so you know which one comes first, which one comes second. And then down at the bottom here, we want the chroma second. We can't see it, it's underneath my head. But we can pick a color. So typically we choose that color first, and we put like a little bit of sand. You'd be putting like a little bit of sand in this, or soil in this pocket, and then compare it to this color and this color. Put a little bit of soil in here and compare it to this color and this color, and try and figure out what color. If you decide on this one, then you have 7.5 YR, value 5, and then underneath my face here it's chroma 6. And that's how you would write it over here. And that happens to be this spot, which is strong brown. So that's how you'd write it in your profile. Strong brown, 7.5 YR 56. And then you would say whether it was dry or moist, because soils have different colors depending on whether they're wet or dry. The next thing after the color is the mineral texture. So color and texture are the ways that we distinguish between different horizons. So knowing the color and the texture is the two most important parts of each horizon's description. Typically, we categorize mineral soil particles by size into 3 classes: sand, silt, and clay. So you can see here, clay are any particle smaller than 0.002 millimeters. They are tiny. We can't feel them. They're so tiny we can't feel them on our fingers. They're so tiny we can't feel them. If you put clay on your tongue, it just feels smooth. If you put clay in water, it remains in suspension for a very, very long time because those colloids stay in the water column. I've had clay stay in the water column for days. And then on the other side, anything from 2 millimeters, if it's greater than 2 millimeters, we consider it gravel, not sand. So it's not soil. Down to 0.05. So that's a huge amount of difference is sand, and anything in between. So 0.05 to 0.002 is silt. So sand feels sandy on your hands. Silt feels smooth like clay on your hands, but gritty on your tongue. These are like the old classifications that we used to use, and then we've added these numbers to them in more recent years, and we have even more specific measurements that we're going to use with hydrometers as we go. So you can look at them underneath microscopes. If you still have your handmade microscope, I recommend looking at your soils. They can be quite interesting to see, like, are they made up of quartz or sand, or do you have other random interesting pieces inside them? We then give names to our soil textures, whether it's clay, sandy clay, loam, silty sand, based on what percentage of those 3 size classes we have. We will use a Imhoff cone or a homemade version of an Imhoff cone to determine what our soil percentages are and find exactly what texture we have. But in the field, which is what most soil scientists are using when they're roughly categorizing their horizons to start with, is a hand finger test of the texture using these rough categories. And then once you bring it back to the lab, you can do a more specific percent calculation. So here are the types of percent calculations we do. This is a proper Imhoff cone here. We're going to use a jar at home. It does not as accurate, but it'll do the trick. And then this is a hydrometer. I'm going to do a demonstration of how hydrometer works. But both of them are measuring the percent based on how quickly these two things drop out of the water column. So sand does not stay in suspension. It's going to drop out right away. An Inhofe cone measures the percent of the sediment on the bottom, whereas the hydrometer measures the clay particles that are still in suspension. But it's measuring the percent clay, silt, and sand you have based on how fast they become sediment at the bottom. And once you learn those percentages, you can put them on this. And so if you have 55% clay, then you can follow the clay and see, oh, this one doesn't do it. Sometimes they'll have like a little arrow here that shows you which way to go to help you with the triangle. But you can follow 55% clay across, and you can follow silt, 35% silt across, and then this is where we end up. So we have a clay. And it's a fairly silty clay, but it's still a clay. Because if it was officially a silty clay, it would have to be more than 40% silt. So these are the official word classes for these soils based on how we feel them when we do texture. And that's in the lab manual we'll go through by feel. So this is one way you can look at those different word classes. So here are those same word classes that we see on here. And then they have different ways that they feel and how you can do casts and ribbons. So cast if they hold a ball, and if you can like throw it around and it holds that ball, and a ribbon is when you squeeze it between your fingers to make a ribbon over your thumb. I show both of these, how to do these in videos that I've posted. I also go through this key in the videos. This is what you would do in the field. So we're going to do this in our structure and texture lab. We're going to go through how to do these keys a little bit better. And you can key out by feel what texture you have. So you usually typically do these texture feel keys first to try and help you figure out where your horizons are. And then you do the percent ones with the Inhofe cone and hydrometer afterwards to get a more detailed description. So once you have color and texture, those are the two most important parts of the horizon, then we start looking at other horizon features. Mottles are considered a really important one, so they come next. And then we're going to do a bunch of other stuff. These ones are near the end of the description. But because mottles show a lot of information about where the water table is, and that's really important, they're the third horizon feature that we're describing after color and texture. And basically you want to say how many there are. This is based on percentages. You want to say the size of them, and then the contrast. So how different are the colors? And it asks, actually, the contrast is based on how different the value and chroma and hue is. So you have to look up the actual colors of the red parts of the mottles versus the white parts of the mottles. And if there is a greater than 2 value units between them, then you're into distinct. If it's the same value units, you're faint. And you sort of, this key, I don't want to read the whole key out. You guys can do this. But you're looking, and you would include the colors. You would write down what colors your mottles are as well. This is how you look at the percentages. They've given you an idea here. I like this diagram. One second. Because each of these squares, this is 15% mottles, this is 15% mottles, this is 15% mottles, and this is 15% mottles. They're just showing you what it looks like with different sizes, and they've done that in every single one of these. So this whole square, all of this is 20%, all of this is 15%, but each one of these subdivided squares is also to show you what it might look like in different situations. And you compare your model pattern to one of these model patterns to try and get an idea of what % models you have. After you do models, then we're going to move on to soil structure and consistence. The structure is the aggregation. So those soil particles, sometimes they sort of clump together. Sometimes it, like sand typically has no structure, it's just loose. But sometimes they clump together, they're called peds or clods. Distinctness, size, shape, and arrangement of those clumps is how we define structure. The strength of them is the consistence. So primary soil puddles are the sand, silt, and clay, and then how they clump together. So here is a good picture of some peds. So this one has really small peds. This one has quite large peds. Like some of this is structureless and some of this has structure. This one's pretty structureless, but there are some peds in there. So this is a lot of peds, hardly any structureless stuff. You'll see all varieties of different kinds of peds. The grade is how distinct they are and how durable they are. So can you actually see them? And then can you pick them up? And then the class is basically the size, and there's numbers that go with that in charts that I have in your handout for your lab. The shape of them, I think I have that on the next page, but structureless, granular, blocky, platy, columnar, and prismatic are the different shapes you can get. Here we go. So structureless obviously is just sand through your fingers, platy, flat plates. The difference between columnar and prismatic is basically like this cap on the top here versus this flatter here. There's also a slight difference between structureless where it's single grain like sand and amorphous where it's just this like clump of nothingness, more like a clump of clay. They define them both as structureless, but then you can additionally define it as single grain or amorphous. An example of granular, you have really small, tiny peds. It's not structureless, but they're tiny, tiny. Once you get into the blocky, you're looking at whether they're angular or subangular or rounded. Here's a good example of platy. You typically see this where you have compacting, like clay-based soils that are compacting rather than soils where the particles are bigger. Columnar versus prismatic. There's a good picture of the rounded tops. And here's a chart to put it all together where we have those size classes and the words and the general type, kind, right? Put everything together in one large chart. Again, here's everything together in one large chart, but with some pictures for you. So consistence is how strong that soil structure is. So the degree of cohesion and adhesion that those soil particles have for each other. The resistance to deformation or rupture is the technical way of saying it, but I like to call it like the strength of the soil. They often talk about soil resistance, soil consistence as resistance to failure, which I think is an interesting way of putting it. You're going to add stress to the soil to see if it fails under that stress. Wet consistence is my favorite one because this is where you get to play with mud. And you're basically taking a little bit of soil between your two fingers and applying pressure and seeing when you pull them apart if they're sticky. So this is getting a pretty wet, like not soaking wet, like you need to, like you're trying to get like a plasticine consistency, maybe a little bit wetter than that. And like sandy soils, you'll as wet as you get them, nothing's going to stick to your fingers. And clay soils, you can actually start to get like them sticking and leaving little trails. When you have a soil that's moist but not wet, then you can see how, and this is you need to do with PEDs, by the way. You're seeing the structure of the soil, how strong it is. So you're taking a PED and you're seeing if it fails with that pressure. So you're going to take one of those PEDs and you're going to add force. So if it's loose, there's like, you pick up the PED and it just falls apart. But if you can crush that PED really gently between your two fingers, you have something that's very friable. If you can't crush it between your fingers, but you need to like use your hand, that's when you're friable. Pushing on it with a hand is firm. Very firm is like you put it on the ground, you're standing on it, and it's still not crushing. This is a pictorial version to help you remember the difference between loose, friable, firm. I like pictures. Dry consistence. Now we're taking the dry PEDs instead of moist PEDs and attempting to break them. And this particular key is very precise about whether you're using just between your fingers, or if you need to use your hand, or if you have to like stand on the PEDs. While you're doing the consistency, it's good to look at the plasticity as well. And this is basically adding enough water to make the soil moldable. And if you, if you have a clay, you'll very easily turn it into a moldable ball. That's where we get clay from. If you have sand, you might not be able to do this. If you have a silty, loamy sand, you may be able to do this. How well you can form a 4mm to 2mm ball gives you an idea of how plastic, how moldable your sample is. Next in our line, after you do structuring your consistence, you do roots, because plant growth is important. So you're just describing how deep they go, how big they are, and there are more specific explanations of each of these, like micro, very fine. There are measurements that go with that. Very few, plentiful, abundant. There are measurements that go with that. Orientation, it's behind my head so you can't see it, but vertical is up and down, horizontal is straight, and then there's oblique that goes this way. So these roots are vertical, roots that go out are horizontal, and then here are some ones that are oblique. They can go at any angle. In-ped and ex-ped are whether they're growing into the ped. So if you can pick up a ped and there's a root through it and you hold the root and the ped's attached to it, that's in-ped. If they're ex-ped, you like pick up the whole root system and the peds are separate from the roots. So here are those class sizes I was talking about in terms of size and abundance. And then after roots comes pores. Pores are a more difficult one to talk about. A lot of you are not going to have any pores in your sample that are visible, but if you can see when you slice your sample, if you can visibly see little pores, you should include them. We'll talk more about porosity as a function of soil infiltration rates later on in the system, like when we talk about density. But for now, if you can see pores in your profile, you should record them. Again, we have specific measurements on the abundance, the orientation, the distribution, continuous, so like, are they in the whole horizon or only patchy? What size are they? And what type they are. There are very specific measurements for all of these. So after you've done roots and pores, then we go through the rest of these horizon features. So we already did mottles earlier because mottles are so common and so important to knowing where the water table are. They're done third. and then we come to the rest of them in the order that I have them written here. You probably won't see these. The reason that they're last is because they often just don't exist in soils. They're very specific to specific soils, but will help you identify what subgroup you have. If you have these, or depending, like vertisols would almost all have clay films, for example, because of slip and slacks. So another word for clay films are argillans. They're often a different color than the inside of the ped. So if you have a ped and it looks nice and smooth, and then you break it open and it looks different on the inside, you probably have a clay film on the outside. And because they're clay, they're shinier because the particles are smaller. As I was saying before, slick and slides are a specific type of clay film. So all vertisols would have clay film. This is an example of a clay film on a sand grain, and you can see they're slightly different colors. This is another shiny clay film on the surface of a ped, and it's again probably a different color than the one inside, but I don't actually know because they only show you this picture. Here's examples of slick and slides in a vertisol. You can see they're like layered. You can see the layers of them from the cracks. Just like all the other things, there are specific terminology we use. So what percentage, few, common, many, continuous, how thick they are, and we have measurements. We often will describe their location, so you'll say how many, their description, and then you only see them in cracks, you only see them on ped surfaces, you only see them in voids or channels. Next up is concretions. These are cemented soil particles. So it's not a rock, it's soil particles that have been permanently cemented together. So usually we do a slake test. We're not going to this year because it's just difficult to do at home. But you take peds and you put them in a little basket and you dip them in and out of water. And almost all peds will eventually slake, but a cemented ped will stay together. You need to take a hammer to crush it. And when you do, you see that it's just made out of sand or silt. It's not a rock, but it's been concreted together. So there's tons of different kinds of concretions. The most common one around here are ornsteins. They happen in podzolic soils from iron accretions. And again, we're going to describe the concretions with all of these things. There are several different kinds. Ornsteins are iron oxides. In limestone soils, we get actual proper cement. You can also get casts from animals that become concretions. This is a durinode, and this is an ornstein. Again, abundance, size, location. Are you finding them specifically throughout everything or only around roots? What shape are they? Spherical, oblong, irregular, plate-like. Next one are carbonates. So these are specifically calcium carbonate. So that might form chemically. It might be old animal shells. It might be a limestone part of your soil. Again, we're going to describe the same things we described with the concretions, but specifically towards carbonates. Right? Looks pretty similar to our last one. One of the things we use when describing carbonates that we didn't when we're describing other concretions is effervescence. Because they're calcium carbonate, do they effervesce? How much do they effervesce? Basically, this is how pure is the calcium carbonate. So it recommends 10% hydrochloric acid. That's standard in the field, but because you guys don't have hydrochloric acid at home, I'm assuming, the acetic acid vinegar does work, not quite as well, but it will be good enough for you guys to discover if you have calcium carbonate present and if it's a strong reaction or a weak reaction. The rest of carbonates is very similar to other concretions. Is it continuous or discontinuous? So these are ways homogeneous versus non-homogeneous. I love that it's non-homogeneous and not heterogeneous. If it's streaked or banded, if there are streaks, what direction do they go in? If it's spotted, what shape are those spots? So if it's discontinuous, like this is discontinuous, these are spotted. Sometimes they're in like little nodes that sort of follow veins. You're describing it based on, but using these specific terms, right? You're not just describing using your own words. This part's the same, abundance, size. They try to keep things as consistent as possible across the different things that are out there. Then we're on to coarse fragments. This is something that's actually quite common, is when you have rocks and pebbles and gravel and boulders in your soil. Because North Bay is on the shores of glacial Lake Nipissing, we have a lot of glacial till in North Bay, and where there's glacial till, you frequently get coarse fragments. It's quite common to be digging in a soil pit and then finding these large rocks. You will probably find some smaller gravelly bits as well. Either way, they're coarse fragments. Anything greater than that sand that's 2 millimeters is a coarse fragment. Because they're rocks and not soil, they don't hold water. That's one of the reasons that 2 millimeter diameter is in place, because sand can hold water. Coarse fragments, water just flows right through. The words we use to describe them are pebbles, gravel, cobbles, stones, and rocks, and we'll go through that a little bit more. This is my favorite part of coarse fragments, is the terminology. We'll look at how much of the soil. So again, this is a beautiful diagram to give you an idea of how much of your soil is coarse fragments. You have, and these are 2 different examples of 5%, 2 different examples of 25 based on whether you have large or small, 2 different examples of 60 just based on slightly different sizes. So this is me making a chart again to try and help you with the terminology, because if we have less than 8 centimeters in diameter, so that 2 millimeters to 8 centimeters is all called gravel. And then if it's between 8 and 25, we call them cobbles. And if it's greater than 25, they're stony, unless they're really big, like greater than 60. We sometimes call it bouldery, but it depends. If the boulders, like if you only have one boulder, you probably won't call it bouldery. But if you have all of your coarse fragments are greater than 60, you might use the term bouldery. Chert is a type of coarse fragment that is quartz that forms like a concretion. So if you have specifically chert, then you call those coarse fragments cherty. Most of our coarse fragments are rounded because they're glacially deposited. So we have rounded and sub-rounded. We don't typically have angular, but if you did, you can have angular that's other than chert. And they just call it angular gravel rather than gravel being smooth, and angular cobby because cobbly is smooth. And then you can also have flat and thin. So you have rounded, irregular, or angular, and then thin flat pieces. So when they're flat, then you have like channery, slaty, flaggy. It's still stony. If it's big, no one cares what shape or size it is. It's big. But here you need to know whether your rock is slate, shale, or limestone or schist. Now, way at the end of our soil profile description, we finally get to those horizon boundaries. And we talked about this in the previous lab, about how to describe these horizon boundaries. So you should be doing this out in the field because that's where you're going to see your horizon boundary the best. Take pictures. This one, I love this one. So this one is quite abrupt. Like it just, there's a very line here, less than 2 centimeters. That's abrupt, right? It's very distinct. And it's forming these kind of waves, right? That is irregular. Pockets are deeper than they are wide. If the pockets are wider than they are deep, so if it went more like this, then you'd have wavy. Because this one is so weird, like this one deep one is deeper than this is wide, that's called irregular. And then you can sometimes have pieces that are broken up. And I think I have another picture of that on another slide. You also need to measure the depth of your horizons. So you need to figure out where, this is a good example of a horizon that's not as distinct, because here you definitely have that horizon, and here you definitely have this one, so you have quite a wide margin where that horizon boundary is. You can still see that it changes, and it's pretty easy to tell, but there's a much wider difference there. Some boundaries, it's so wide it's difficult to choose, and that's why we have things called like BC, is that layer between. You have a B layer for sure, a C layer for sure, and the horizon boundary is so wide, we've called it BC horizon. You want to measure, you start your depth, so you need to figure out where your LFH layer ends, and that's 0. And then you need to get where the deepest part you can see that horizon is, where the shallowest part you can see that horizon is, and sort of an average. If this starting point of 0, like you have all organic up here, if this is more than 40 centimeters, you have an organic soil. Even if after 40 centimeters you hit mineral, if you have more than 40, you have an organic soil with a mineral substrate. If you have less than that, it's all just LFS. It's not an organic soil, it's a mineral soil with a large organic layer on top. So as I was saying, you need to measure the deepest and narrowest part. You can see here, this one's a good example where you have like little dips in the horizon here. That's again irregular. And lastly, we have reaction. So we're just finding the pH of the soil. And this is where your newfound pH indicator will come in handy. You probably aren't going to go to the extremes. Most soils, to enable to support life, most soils are in that 5 to 8 zone. Beyond that, they become quite toxic. Life does not like to live in extremely acidic or alkaline environments. So your homemade pH indicator, it's not very detailed, but it will show you the change between those mild pH changes of 4, 5, 6, 7, 8. So then you put it all together and you write it out. Remember, it has to go in this order. All those different things that you've just recorded about each step. In the lab handed, I think I've made a table where you can put some of the things to help you organize it yourself. You might find a better system that works for you, so you have all these things written down in the order they need to. Here's an example. What I usually do in class is I give you guys the keys to the soil orders and the keys to the grade groups, and we spend some time using this particular soil profile description to try and figure out what kind of soil it is and to name it. Because I can't do that with you in this particular way, I have given you this particular example in your assignment, so you have the answer to this that you can go and look up. But I don't want to give you the answer today, so you have the option of going and looking it up. But you can see it's very similar to the assignment I want you guys to do. You've got your horizon name, the depth. So see the organic one ends at 0, whereas the mineral one starts at 0. And then in the order we went through, color name, color code. This is moist. Color name, color code for dry. They've told us if there's organic matter and what it's like, and described all the different things in the order. Here's our boundary. Here's how thick it is, and it's acidic, right? So here's a BFGJ layer. What do those symbols mean? Basically, just based on this horizon part, you can probably classify the soil. Color, description, moist and dry. The texture, and then it goes through all of those things that we went through. Smooth boundary, how thick it is. It's also acid. This is the sort of thing I'm looking for your soil profile. I also want you guys to draw a sketch of your soil profile. So I want an actual photograph so that I can tell if you're actually right or not. I want a photograph of your profile. I want a sketch. I'm not looking for anything like, I don't care if you're not good at drawing. Do your best for me, right? And beside your sketch, you should have your horizon names. These are just general horizon names. These aren't actual horizon names. And you should have your measurements. This sketch is trying to show you like different features, different mottles, different size. Maybe these are roots or peds. Trying to, if you can show if you have a weird horizon boundary, you can draw that on as well. So I want all of that, and then I also want you to have your grade group. Oh, I want you to have your soil order. Oh, I forgot to change this. This was 5% last year, but I'm making it 10% this year. I've added a little bit more detail to it than I had last year. And yeah, made it a little bit more in depth. So it's a 10% this year. I think that might be the last slide. I think this is it.